So for today's topic, what we're going to take a look at is the standard form. Last day when we were looking at vertex form, this is what the standard form looks like. So it's when we expand the equation and collect like terms so that we just have three coefficients, one for x squared, which is a, one for x, and then a constant. So we'll talk about some of the advantages of using standard form here. But first, let's take a look at how we get from vertex form into standard form. And what I'm going to do is, why don't we just start here with our vertex form, just to give us some reference for where we're going. If I expand these brackets, I would get y equals a x squared minus 2p plus 2px plus p squared plus q. And now if I distribute that a, I'll get y equals a x squared minus 2 apx plus ap squared plus q. So one thing is the x squared term still has the same coefficient as we did before, which is a. So that doesn't change. But some of the other ones do. This here is going to make up the constant term, the term with no x. So that in ours is going to be c. And this one here is going to be the term for b, the coefficient on the x value. And that's the one that I want to look at here, because it's actually going to help us get some new information out of this. Let's build on this last thing that we just had here. If we have b is going to be negative 2ap, then the reason that's something of interest to us is we can try to figure out quite quickly what's the value of p. So p in this case is going to be b divided by negative 2a, or we could write it like this. And the reason that it's convenient for us to find that is by doing that, it gives me the axis of symmetry, or the x-coordinate of the vertex. So that's possibly the most important thing we've started with here today. If we want the equation for the axes of symmetry, or of course the x-coordinate of the vertex, if we're given a graph in standard form, then what we're looking at is negative b over 2a. So let's try this with a graph. So let's first start by identifying the values here. A is negative 1, b is 2, and c is 8. So if I wanted to figure out the axes of symmetry, or the coordinate for the vertex, I'm going to come up with negative 2 over 2 times negative 1 by substituting it into our formula. That'll give me negative 2 over negative 2, so 1 is the axis of symmetry. Now, how do I go about then finding the vertex? Well, once I know that at x equals 1, I'm on the vertex, I can just use the equation since y is equal to this. So y will be equal to negative 1 squared plus 2 times 1 plus 8. So that's negative 1 plus 2 plus 8, so that'll be 9. So if we were to graph it, then let's start there. We'd go 1 and 6, 7, 8, 9. So there's my vertex. This parabola is pointing down because it's negative. So 1 over, 1 down. There's no additional stretch there. 2 over, I'll go 4 down. So there's a decent set of points to use for my sketch. So something about like that. And the points that I found, again, where I started with, the most important one was to locate the vertex, which was at x equals 1 and y equals 9. And then, since we know where the axis of symmetry is, it's helpful, if we're making a set of values, to go, say, 1 to the right. So that would be at 2. And the next point would be 8. and if I went 2 over, I end up at x equals 3, and this was y equals 5. So you can, of course, do the calculations by hand if you didn't like doing the shortcut like I'm using, where I go over 1, down 1, over 2, down 4. What you could do instead is you could plug it into the value of the equation. So it would be y equals negative, let's start at, let's do 0 here, which is this one. So it'll be 0 squared plus 2 times 0 plus 8. So that'll be gone because I'm multiplying by 0, so I end up with 8. So at 0 the value is 8. And we can do this again here at the next one, at negative 1. So this will be negative 1 minus 2 plus 8, which is 5. So at negative 1, the y value is 5. And again, you'll notice these are the same, and these are the same because of the symmetry. So if you're trying to plot out points, really we only need to do one side, and then we know because of symmetry that they're going to be the same values on the other side, in this case 8 and 5, as there were on the other side. So we'll try this one again. We'll start by finding the value for p if we're doing this in vertex form. So that'll be negative b over 2a. So negative 12 all over 2 times 2. So 12 over 4, which is 3. So the first point I'm going to be looking for is x equals 3, and the y value is going to be plus 10 is going to be negative 8. So now that we have a vertex, that's the first place I'd want to start. So at x equals 3 and 5, 6, 7, 8, negative 8. This one, the a value, which is the same for vertical stretch, is 2. So when I go over 1, I go up 2, and then over 1, up 2. Normally I go over 2, and I go up by 4. But because there's a stretch of 2, I'm going to go up by 8. So here's a sketch I could show you for this parabola. And again, the points I was plotting, if I know where the vertex is, the axis of symmetry, then it's good if we just go in one direction. So at 3, if I go in one direction, the next point is at 4. So I could substitute it in if I didn't use the little graphing shortcut that I've been working with you. And this is going to be 2 times 16 minus 48 plus 10. So 32 minus 48 plus 10, which is negative 6. And if we go 2 over, that would be at this point here, which is 5. Right, so this is from 3 to 4 is plus 1. From 3 to 5 is plus 2. So y equals 5 times, 2 times 5 squared. Oh, having some pen troubles here, sorry about that. 2 times 5 squared minus 12 times 5 plus 10, which is going to be 50 minus 60 plus 10, which is 0. So there's a good set of points to work with, and this is all on the right side of the axis of symmetry. So again, if I wanted to figure out what was on the left side, at minus 1, that's 1 less than 3, and minus 2 would be 2 less than 3, and take on the same values because of the symmetry involved. So this would be if we had to actually find the points by hand. Of course, if you're graphing them, you could also use the vertical stretch factor like I've been showing you. So we'll tackle a couple word problems here before we finish. A diver jumps from a 3-meter springboard with an initial velocity of 6.8 meters per second. Her height after leaving the board can be modeled with this quadratic equation. So we want to know what maximum height is the maximum height she reaches, and when does that happen, and at what time did they hit the water. So the first thing we can do is if we want to know about a maximum height and when that time was, really what we're talking about there is a vertex, right? If we picture this person bouncing off a diving board, and again you'll have to forgive my artistic skills, but they bounce like that, and there's my parabola that the diver travels in. So the maximum height and the time they hit it is that vertex right there. So if I want to know where is that value, let's start by finding the vertex, which is going to be negative b over 2a. So for us that'll be negative 6.8 over 2 times negative 4.9. And I get a time of 0.693, and I'll round it here to 339 seconds. And if this is when it happens, that means I know what time it was here when she hit the maximum. So if I want to know, I just plug it into the height. So her height at that maximum is going to need a calculator here for this, but in my calculator I haven't rounded it just to make sure I keep the most accurate answer. But it would look like this, and it's going to be 5.36 meters that she reaches if we answer to 2 decimal places. So now we know the maximum height and the time it happened. The only thing we haven't answered is what time it hits the water. And for now, all we can do is sketch, because we've just been working on plotting these graphs. So I'm going to show you what, since I want to be very clear about what it would look like. My artistic skills might let us down. This is what the graph of that diver would actually look like. And let's zoom in on a better picture here. I don't need to go that far below 0, because that means she's already hit the water. And let's say 10 here for the top. So there's a pretty decent picture of the diver when she jumps. Oops, sorry, of course I've forgotten an X there. There. So she starts at 3 meters when she jumps off that diving board, and this is the vertex we just found, which happens just as we said. You can see the down in the bottom corner it shows the points, but you can see here it's right where we wanted it at 0.69 and 5.36. And this is when she hits the water, right here when her height is 0. So we would, if we did a sketch of this graph, then we'd be able to see that, you know, using the picture we can make an estimate. So where the crosshairs are now is about 1.5, and that's 2. So I'm going to guess by looking at the picture maybe 1.7. And of course with a bit of technology here I can also see that this is 1.73 might be a better guess, but we'll call it 1.7 seconds. Of course we will have better techniques coming up later on, so all we can do now is estimate it. So we put she, oops, do a better job of that. She hits the water at about 1.7 seconds. Okay, so this question will be similar. It says a farmer has 400 meters of fencing and wants to enclose livestock against a barn. So let's just stop here and draw what's going to look like a, well, not really look like a barn, but we'll say that this is the farmer's barn, because we all know barns are red. And he has 400 feet of fencing, and he's going to go like this. To enclose his animals. So we can come up with an equation here to show us how much fencing they've used. So I have 400 feet. And when I build this rectangular enclosure, then I'm going to have to use the same side here as I do for that one. Otherwise it's not going to link up properly. If it was slightly smaller, that wouldn't close the gap, and if it was longer, it would just be a waste. So assume that they're the same side. That means I had 400 meters to start, or sorry, 400 feet, and I've removed 2 of whatever that amount is. So this is how much I have left to make up the width of that enclosure. So I can come up with, if I want to come up with an area, if I want to come up with an area function, the area will be equal to length times width, which is going to be x times 400 minus 2x. And this will give us 400x minus 2x squared. And I'm going to write this in standard form since that's what we're working with today. And what we'd like to do is maximize it. So the largest possible area, if we were to graph this, it's dropping down. I'm going to just guess that it's going to look something like this. Something like this. Because at time 0, or sorry, that was the last question. If we use an x value of 0, meaning we have no length to the fence, then there'd be no area. And over here, this would be when we've used up all of it to do the width of the fence, and none here for this this side of the enclosure. So this is what we're looking for, is what's the maximum possible area. So this would be my area, and this would be my width. So that's the vertex I'm looking for. So that will be negative 400 over negative 4, which is 100. So I know that this happens if I use an x value of 100, meaning the width here should be 100. Then I can quickly figure out what's the height going to be, because I can substitute it into this equation. So 400 minus 2 times 100. I was left with 200 feet of fence left for this piece. So the largest possible area is going to be 100 by 200, and that's going to be 20,000 square feet.